Hello everyone and welcome to this tutorial. So today I will be showing you how to model a three-phase fault in IEEE 14 bus system in EMTP software. So if you find this video helpful, do not forget to like and subscribe to my channel. So let's get started. First of all, the structure of the 14 bus IEEE system is as follows, and as you can see that in this structure we have 14 buses, some loads, some generators, and yeah, so on. The R values that you see over here show the relays for our structure, directional overcar relays, and in this study we are not going to need them because we are just going to do the fault analysis, but later on I will need them for a study of mine, which is about determining the parameters of overcar relays. But in this tutorial, we will just neglect these R values over here, for example, R36, R35, and so on. We are not going to need any of that. And yeah, L shows the number of lines, and B shows the bus number, and we have the generators over here, and this one shows the loads, and yeah, the parameter values for our IEEE 14 bus system is shown in this table. You can find this table online, and as you can see, the value of line impedance, resistance, reactance for each line is indicated over here. For example, for the first line, it's the resistance value is 0.01938, and yeah, so on. We also have the half-line charging susceptance values over here, and all of these values are indicated in per units. We have the megavolt ampere rating of each line, and so we are not going to need these values for this study, but yeah, it is written here anyway. The base voltage for the IEEE 14 bus system is 69 kilovolts, and the base power is 100 megavolt ampere. So let's get started. First of all, I'm gonna open EMTP, and here let's open a new project, new design, default design, and yep. Okay, first of all, we're gonna need a generator. So let's have this picture in mind, where I'm going to start from the first bus. Where is the generator? In sources, click on AC voltage 3-phase. I'm just gonna rotate it to left. So I'm gonna name this generator 1, and so here I'm gonna indicate all values in per unit, so that I won't have to deal with per units at the end of my simulation. Therefore, I'm gonna just indicate everything in per unit and enter all values in per unit. However, if you like, you can just enter the real values for your parameters over here. For example, if you want to enter the real values, you're gonna have to type in 69 kilovolt RMS line to line, okay? But here I want to use the per unit values, and therefore I'm gonna enter these values for my 3 phases. So this is in kilovolt, and if it's multiplied by 1000, it's gonna be 1 RMS line to line per unit value. Okay. Yeah, the rest of the values are all right, I think. And Yep, I don't need any scopes, and I don't want it to show the values over the generator, so let's just have that one. Okay, so now I'm gonna need a bus, the first bus. Draw a 3-phase bus, and this is my first bus. Okay, so and yeah, let's have the second generator, and I'm gonna rotate this one as well. And this one, for example, has a value like 0.8 per unit. Okay, so it's not indicated what is the value of each generator in IEEE 14 bus system, so you can just customize your own structure and enter your own values, and that'll be fine. Yeah, that's all. Okay, I just don't want to show the values over the structure, you know. When I click on this value checkbox over here, we're gonna see the value for a generator written over it, but I don't want to see that. So attributes, I'm gonna uncheck this box, and yeah, it's better like this, I think. Okay, let's draw the second bus, and this is my second bus. Okay, so let's have a look at the original structure. Yeah, okay, there is first bus, there is second bus, and they are connected by a line, by line 1. So let's just draw line 1. I'm gonna connect them to their buses. So for lines, I'm gonna use the RL branch. Because a 69 kilovolt IEEE 14 bus system is a transmission line, and you know that in the transmission line the value of line capacitance is very low. So for my study, I'm gonna just neglect that one because I don't want my structure to be very messy, and that's it. So I'm just gonna go ahead and use the RL branch over here. However, if you like and if you want a more precise you know, results, you can use other options here. For example, you can use, let me see, RLC branch is not going to be right because in transmission lines C is not in series with R and L, so this is not the right option to use. But you can use this one, okay, which is the P, you know, structure of the transmission lines, or yeah, so on. You can use this one, or you can use in lines, you can use the CP line 3-phase. Here you can also determine the value for RLC, and another option is that you can use frequency dependent line. Well, I personally don't recommend using this one for fault analysis because I don't think it is worth the trouble you're gonna have. Because this is the most precise structure that you can use for lines, but I don't know, it depends on what study you are trying to conduct. But this makes the simulation very complex, and you're gonna need a lot of time to run this simulation. So for my study, I'm just gonna use the RL branch over here. And for each line, I'm gonna use 2 RL branches, because I will put a fault in the middle of each line. Okay, so where is RLC branches? Yeah, here. So in RLC branches, I use RL branch. Okay, let's see what's the value for first line. It is, the resistance is this much, and I'm gonna divide it by 2, because as I said, for each line I will be using 2 RL branches like this. Let me just demonstrate that, like this, and I will put a fault in between, in the middle of each line. That's why I'm gonna need 2 RL branches for each line. Okay, and this is specific to my study. So let's see what is the value for the first line. Let me just bring the calculator. Okay, I'm just gonna divide this one by 2, and this is the value for first line. I will enter that over here. Okay, and what is the value for L? The reactance value is this much, but this is the reactance value, so I'm gonna have to just get the L value, inductance value, from this reactance value over here. And to do so, I'm gonna need some calculations. Just enter this value over here. And divide it by 2 multiplied by P. And multiplied by the frequency. By the way, the frequency that I'm using for my study is 60 Hertz. And we're gonna have this value, and just gonna multiply it by 1000, because I want to indicate the values in millihenries. I'm gonna get this value and divide it by 2, because I will have 2 branches. And yeah, this is the final value. Let's just enter it over here. 547. Yeah, I think that's enough. Just change this to millihenries, and my nominal frequency is 60 Hertz. Yep. I don't need any scopes for now, so let's just be okay. I don't want to show the values over the line, so just uncheck that box. And yep, that's all. So I'm gonna just copy and paste this line, and this one is line 1, and this one is RL1, which is the other half of the first line. Yeah, that's all. So let's just connect these to each other and to the buses over here. Yeah. Okay. So I'm not just gonna add the load for the second bus. So for that one, I'm just gonna use the loads over here, load models. From the load models section, I'm gonna use the RLC load. Okay, let's see. The voltage is gonna be since the voltage of this bus over here is 0.8 per units, because this is connected to the generator. So I'm gonna set a value for this one, and I'm gonna set just 0.8 for it as well, and just indicate it in volt RMS line to line, and that's gonna be 0.8. Yeah. So for the active and reactive power, you can enter your own values. There is no limitation on that. There is no data on that, and you can just enter your own load values over here. But since everything is in per units, these also must be in per units, so they should be divided by 1000 megavolt ampere. And for this one, I can enter a value, for example, 0.1112 and 0.075, and this has a power factor equal to 0.83. Okay, so from the attributes, I don't want to show any values over it, and yep, this is my line. Let's just rotate this. This is my load, and let's just rotate that as well. And yep. And let's see what else we have. So we have the third bus over here. Let's just also model that one. Okay, draw a 3-phase bus, and this is my third bus, and it has a load. And okay, let's just copy this load over here. We don't need to bring a new one. And for example, this one has the voltage equal to, for example, 0.9 per units, and the power for that is 295 and 166. Okay, and yep, that's all. So the reason that the load model asks for the voltage value is that because it's going to need the voltage value to calculate the current that each load just derives or attracts from the system. Okay, let's just connect this one over here. And what else does it have? We have the third line between these two buses. Okay, RLC branches and RL branch. Okay, what values we're gonna need? The third line. Divided by 2, and this is and for this one divided by 2 and multiplied by 1000. Okay, and this one is in milliharmonies, and the frequency and no attributes, and this one is named line 3, sorry. And yeah, I'm just gonna copy and paste that to get the second half, RL3. And okay, and the rest of it is done in the similar way, and there's no difference, just that for some lines we don't have the our values. So we are, for those lines, we are just gonna use the RLCL model, and yeah, no other points. So because it takes a lot of time to just model whole structure over here, I already have a ready structure in EMTP, and I'm gonna load that, and we are going to do the fault analysis over that one. Okay, so let's load the original one, the complete model. Okay, this is the complete model, and as you can see, I have modeled everything over here, the 14 buses, the loads, and everything. Okay, so here I have put a fault. Let me just show you how to model this three-phase fault on this part of the line. So I'm just gonna delete these ones. To model a three-phase fault in EMTP, you're gonna have to go to the switches, and from the switches you can choose whichever you want. By the way, I have a separate video on how to model a fault in EMTP, and you can check that one as well. I think it will be very useful. So from here, I choose ideal switch. You can choose whichever you want, but for my study, I'm just gonna select the ideal switch, and I'm also gonna need a ground. Where is the ground? Okay, here, ground, and yeah, let's customize the parameters. So this switch over here can be used single phase or three phase, and it automatically switches to a three phase when it is connected to a three phase line. So let's just connect this one to here, and I assume that it closes in 60 milliseconds, and it never opens after that. Okay, no scopes for now, and yeah, I'm gonna just connect it to here, and as you can see now it has changed to a three-phase switch. Okay, let's just run the simulation, and from scopes over here I'm gonna, for example, show the I value for this line, and you can also show the V values. I'm just not gonna select that one for those, but you can show the V values for your generators. Okay, and you can also show any I values on any part of the system. Okay, and let's go to the simulate, and in simulation options I'm gonna change my simulation time to 32. And yes, that's all. Let's just run this one. And as you can see, the simulation takes pretty little time. But if you used more complex lines over here, it would take much more time. So I'm just gonna review the results in the scope view. Okay, here in scope view, I'm gonna show the branch current. I'm also gonna show the, I don't think there is, okay, the generator voltage. Let's see them. And yeah, as you can see, the fault happens in time 60 milliseconds, which is over here. And for example, the maximum current value before the fault, three-phase fault happened was 0.6 almost. Okay, after the fault happens, the current value increases to 0.9. And this is because basically we have less resistance in our system after a fault happens, especially when a fault without any resistance happens. Let's see the voltage. The voltage is the maximum voltage is 0.8. The value I set for each generator was 1 per unit RMS line to line. So if you just convert it to one phase and peak value, it's gonna be 0.8. And yep, that's all. So if you want, you can also export the results to a text document from here. Fault results. And to a text document over here. And as you can see, it shows the time, the line current, and the generator 1 voltage. Yep, and that's all. Thank you very much for watching this video. And if you have any comments, any questions, you can just comment them below this video. And see you in the next tutorial.